In our previous video, we converted points from polar to rectangular form. Now we're going to convert equations from polar and rectangular form. And these are going to be the four relationships that you need to store in your memory banks. If you don't already know those from our previous video, write those down because I'm going to be pulling these in to a lot of the conversions that we're going to make. We're going to start with some of these rectangular equations. These are equations in the form of x and y, and we're going to convert them to polar form, which would be in terms of r and theta. So if I start with this first one, we have 2x plus y equals 4. We have this linear equation. And so what I know is that if I have an x, I know that x is equivalent to r cosine theta. So I can substitute that in. And then if I have a y, that's equal to r sine theta. And now we see in both terms, they both have an r. So I'm going to factor that r out to the front. And then lastly, I'm going to isolate the r by dividing by this stuff on both sides. So I'm going to have r equals 4 over everything. And this is actually going to be our polar form of this equation. It's not pretty. The reason it's so ugly is this is an equation that is more conveniently written in rectangular form. That's why we use rectangular to draw lines. But there's going to be our polar form. Why not be useful? That's how you do the conversion. Now let's look at our second example. If we're doing y equals -3, once again, if I see the y, I know that y equals r sine theta. So I'm going to make that substitution. And then I'm going to divide both sides by sine theta to isolate the r. And right here, we can simplify this one step further. We have the reciprocal of sine theta. And if we know our trig functions fairly well, we know the reciprocal of sine theta equals cosecant theta. And that's that one in polar form. Now let's look at this quadratic. We've got a parabola, looks like our quadratic parent function. And I'm going to start it the same way. I'm going to make my substitutions. I'm going to substitute in r sine theta for y and r cosine theta for x. Now that I'm here, if I'm squaring this entire term, I've got to square both the r and the cosine theta. So let me just go ahead and do that. Remember, the goal is to get the r by itself like it is in both of these two equations. So I'm going to divide by r on both sides. That's going to cause this r to cancel. And that's going to leave me with sine theta equals r cosine squared theta. And then by dividing by cosine squared theta on both sides, we're here. From here, you got to be fairly decent with your trig identities. I know that if I have sine theta over cosine squared theta, that sine over cosine here, that's just going to be tan theta. And then right here, this 1 over cosine theta, that's just going to be secant theta. So this equation in polar form would be this. Now we're going to do 3 quick examples. On these, I would encourage you to pause the video, try it on your own, write it out on paper, see if you can make the conversions, and then hit play and see if you got them right. And so now I have r squared cosine squared theta plus r squared sine squared theta equals 25. Kind of like one of the problems we did on the last slide. See how both of these have an r squared in it? Let's factor that r squared out to the front. And I think we'll see something that should trigger a memory for many of us. That's a good memory or a bad memory, I don't know. But if I factor out that r squared, look what we have. We have cosine squared plus sine squared. If I have cosine squared theta plus sine squared theta, that's our Pythagorean identity. And we should know that that's equal to 1. So this is really just r squared times 1. And anything times 1 is just itself. So we have that r squared equals 25. Or we could take the square root of both sides and get that r equals plus or minus 5. So in polar form, the equation r equals 5 is equivalent to the equation r equals -5. Those are the same equation. Those would both be a circle with a radius of 5. Let's do round 2 right here. First step, you probably see what we're doing. Now we're going to do it just like last time. Let's factor out our r squared. And then we know that cosine squared theta plus sine squared theta equals 1. Now we're almost there. I've got an r squared here, but I also have an r here. So I'm going to divide both sides of my equation by r. And then we're done. That's the equation in polar form. Here's our last example of this type before we move to our next type. So I'm going to make my substitutions. Now notice on this one, we have an r on both sides of the equation. So I'm going to subtract this term from both sides. And I'm going to factor out my r. Lastly, I'm going to divide both sides by all the stuff. And that's going to be that last equation. Now, let's look at our other type of problem where we're actually going to start in polar form and convert to rectangular form. I've just got a couple of examples here. So if I start in polar form, what we need to recognize first off that secant theta is equal to 1 over sine theta. And so if I take this and multiply both sides of my equation by sine theta, we have r sine theta equals 2. Well, r sine theta, if we remember r sine theta, that's what our y coordinate is. So we have y equals 2, and boom, we've converted this equation to rectangular form. This would be a horizontal line through 2. Now, let's do this last one. So we have r equals 2 cosine theta. And I want to include one like this because this one's a little bit of a party trick that you probably wouldn't recognize unless you were looking for it. But my first step on a problem like this is I'm going to multiply both sides of the equation by r. And note that right here, we have r cosine theta, which is equal to x. So we have r squared equals 2x, but we're not quite in rectangular form yet because I still have an r squared, right? And so what we do is we need to rewrite the r in terms of x and y. And I didn't copy it over to this slide, but one of our relations that we learned is that r is equal to the square root of x squared plus y squared. It was our Pythagorean theorem. It's how we found r. So if I substitute that back into my equation, we're going to have r squared equals 2x. And so if I actually simplify, I know that the exponent and the radical are inverse operations. So we have x squared plus y squared equals 2x. And we actually at this point have this in rectangular form because we've written it in terms of x's and y's. But if we wanted to get some bonus points, here's how we do it. I would recognize that this is actually going to end up being a circle. And so what I did is I subtracted 2x from each side. In our way that a lot of times we rewrite our circle equations in what we call center radius form is I have to complete the square. So I'm going to turn that into a -1. I'm going to divide it by 2 and square it. It means I'm going to add 1. Anything I do to one side, I do to the other. And then now that I have this perfect square trinomial right here, I know that that's going to factor to being x minus 1 squared. We still got my y squared, and that's equal to 1. So what this is this is a circle that has a radius of 1, and its center is going to be at 1, 0.